Welcome to Mathematics 2 once more. In the last video we've talked a little about directional derivatives. In this video I'll show you a brief example. You already know that one example, but we will now apply the techniques that we learned, partial derivatives, directional derivatives, to this example. And hopefully find out where optimal this example may be along the given lines. So let me give you the function first. The example is a function from r squared to r, defined as f of x1, x2 equals 1 minus x1 squared minus x2 squared plus 3x1, x2. And we will be interested in the behavior at the origin, so x star will be the point 0, 0. Let us first have a look at the partial derivatives of that function. So df dx1 at x star. Differentiating that function with respect to x1 basically means we treat x2 as a constant. So every term that involves x2 only will vanish with the differentiation. Every term that also involves x1 will be differentiated according to the usual rules. So what we get is minus 2x1 plus 3x2. And of course we can do the same thing with respect to x2. The result is then minus 2x2 plus 3x1. So now x2 is treated as the variable and x1 is treated as a constant. Okay. If we're working along these lines, then of course we can also compute the second partial derivative. So let's compute d squared f dx1 squared. Then this will be minus 2. And along the x2 line, we can compute d squared f dx2 squared. That is also minus 2. So in particular, the gradient of f is of the form minus 2x1 plus 3x2 minus 2x2 plus 3x1. And you will notice that the gradient at the origin at 0, 0 is also 0, 0. Okay, in particular, if we restrict f to one of the axes, to one of the lines that go through 0, 0 and go in axis direction, then we can see that the function has a stationary point at the origin. And if we look at the second derivative in that direction, then we can see this is negative. So that means we'll have a local minimum along both of these lines. And maybe you remember that we had a look at that function earlier, and that was just the result that we got using more elementary methods. Okay, so let's make a quick note of that. In particular, f restricted to one of the lines, well, either origin plus r1, 0, so that's the x1 axis, or origin plus r0, 1, that's the x2 axis, has a stationary point at 0, 0. So the partial derivative in that direction along that axis is 0 at that point. Both with negative second derivative at 0, 0. That was -2. So that means we can conclude that f restricted to one of the coordinate axes has a local minimum at the point 0, 0, at the origin. Okay, and that works along both axes. On the other hand, we've also already looked at a different direction, namely the direction 1, 1. So let's now have a look at what happens if we restrict ourselves to that direction and look at the directional derivative in that direction. So let's consider the direction 1, 1, v equals 1, 1. And we'd like to compute the directional derivative of f in that direction at the point 0, 0. So that directional derivative is g prime of 0, where g of lambda is defined as f of 0, 0 plus lambda v. So that's f of lambda lambda. You've seen that already, but it's easy to compute it, of course. So that is just 1 minus lambda squared minus lambda squared plus 3 lambda squared. So what we get here is 1 plus lambda squared. And that means g prime of lambda is 2 lambda. And also g double prime of lambda is 2 plus 2 in this case. So what we get is dv of f at 0, 0 is 2 times 0. So that's 0. Again, a stationary point, also along that line. And let's also consider the second directional derivative at 0, 0. Then what we get is just 2. Okay? So this time we actually have a local minimum. So what that means is f restricted to the line 0, 0 plus r 1, 1 has a local minimum at x equals 0, 0. And again, that is consistent with our findings from before. And I was just realizing that actually I made a mistake before. Of course, I think I claimed, here wrongly that f had a local minimum at 0, 0. That is of course wrong, and that should be a local maximum. Okay, again, consistent with our findings from before. Okay, so you can see we can use the directional derivative to get results easily as we would get them for one-dimensional functions as well. But you can again see that even the notion of directional derivatives is not sufficient to capture the behavior of a function fully. So Just to complete the example, let's do one more direction for that function. Let's say we choose 1, 2 to see if that behaves differently. Okay, then we get g of lambda equals, again, f of 0, 0 plus lambda 1, 2. So in this case, we get f of lambda and 2 lambda. And that means the behavior is now a little different. So we get f equals 1 minus lambda squared minus 2 squared lambda squared, so 4 lambda squared, plus 3 times lambda times 2 lambda, that is 6 lambda squared. And the result is, again, 1 plus lambda squared. So g behaves the same on this line as it behaved on the 1, 1 line. And again, f has a local minimum at 0, 0. F has a local minimum at 0, 0 if restricted to the line 0, 0 plus r times 1, 2. Okay, so also along this line, there's a local minimum. Now, of course, what we would actually like to know is local minima and maxima, not just with respect to a single direction, but with respect to all directions. We'd like to understand the global behavior of that function, or at least the behavior in several directions. So what we'd have to do is we'd need a look that somehow incorporates all of these directions at the same time, and maybe not just lines, but also other ways of reaching a certain point. That has been the problem with continuity. So before we go on here and try to properly define what a differential in multivariate functions should actually look like, let's have a quick look at that function here. I did a quick plot. So have a look at that here. That's a plot of a function. 0, 0 is approximately that point here. Yeah, it's not good to see at this point here. Yeah, that's better. So what you can see, what happens here actually is if you're moving in one of the axis directions, for example, parallel to the x1 or to the x2 line, and what you get is a direction that moves here, here. Yeah, so you can see that point is actually a local maximum in that direction. Same thing true if we move here. The function rises if you come from this end here and then falls again. So there's a local maximum here. On the other hand, if you're coming from this point here and walk along the surface through the origin, then obviously that point is a local minimum. Yeah, and if you would choose that direction here, from back there and down here, then again you would get a local maximum. So having a look at that chart here reveals that the point 0, 0 is obviously neither. It's not a maximum, it's not a minimum. Yeah, depending on which direction you move from that point, you either rise or fall in function values. So that characterization is obviously not sufficient. And as I said already, we'll have to think of something else. And we will do that in one of the upcoming videos. So thanks for your attention. And I'll see you in the next video.